Now the next one's to do with capacitors. So can you see? Are you sure? All right. You have two capacitors, 2 microfarads and 8 microfarads, and there's a potential difference across the combination is 40. Determine the capacitance of the combination, determine the charge on each capacitor, determine the total energy stored in each capacitor, and then we have to do some graph. So they're in series and charged.
So it's just 2 capacitors and a battery.
It is that, isn't it? 2 capacitors and charged. The potential difference across the combination is 40. Now what's perhaps a little bit confusing here is the 40 is for both of them, not for each one. And it'll be different for each one. So if you draw it, it's like this. Capacitor 1, capacitor 2, and then there's a 40 volt across the two of them. This will be a V1 and this will be a V2. So you know that V1 plus V2 should equal 40. Huh? Okay. Now, calculate the capacitance of the combination is the first thing. So remember, when it's in series, the formula would be 1 over C equals 1 over 2 plus 1 over 8. Is that okay? Yeah. So therefore, 1 over C would equal 5/8. So therefore, C equals 8 over 5 microfarads. So that's part A done. And that should be okay, right? Yeah. Now, the next part, determine the charge on each capacitor. Now, do you remember I said that the charge on each has to be the same when it's in series, otherwise it's not balanced. So the charge will just be the same as the smaller one, and the smaller one is 2. So remember the formula for charge, Q equals CV. So that would equal 2, but here's the problem. We don't know what the V is, because remember it's the smaller one is 2, yeah. Sorry, I called that one the 2 and I called that one the 4. 2V1, which we don't know. But often the way these things work is that what you did in the previous part is to help you in the next part. So what do we know from part A? We know that the total should be 8 over 5 microfarads. And you remember when I did the proof, I said the charge here and the charge here is the same, but it's the same as the total charge on both of them together. So in fact, I don't think we should be using this. I think we should be using this one here. That way I can use 40. So we have Q equals CV, which equals 8/5 times 40. Now that looks good because that goes into that 8 times. So that is 64. That of course is, remember, it's micro. So that would be micro coulombs. 64. Now I don't remember the question, but I feel like the next question should be what's the voltage in each one. So let's have a look. No, determine the total energy, which is actually easier to do. So do you remember the formula for energy? So that's part B. Part C, energy equals a half CV squared. So that would be a half C V squared. 1280 microjoules. Again, because the C is in micros. Okay? If the capacitor combination is then connected across a large resistor, draw a graph to show how the current flowing through the resistor will vary with the time. So that's actually what we just did recently. Where's my paint? There we go. In other words, if you connect this capacitor to a resistor and let it discharge, what would be the graph for the current? Do you remember it? So here's time, and then here's current. So what would it be? Do you remember what shape? No, it's already charged up.
Exponential increase and then constant.
Yeah, but it's already charged up, so we're just looking at the discharge phase. So it'll just be like this. And then to make sure we get full marks, I'll write in amps here, seconds here, X and Y, and then I'll put in even the formula, which is I equals I0 e to the minus t over the time constant.
Do we need to specify that it doesn't approach zero?
No, just don't have it crossing the axis. Okay, let me